Hi, stats students. Welcome to Chapter 7. So Chapter 7 is an exciting one because now we start using, and I know it feels like we have all along, we start using all the things we've learned so far. So we are going to talk about in Chapter 7 confidence intervals and sample sizes. We have not talked about confidence intervals, but we've talked about samples and how large we want them to be and all those other things. So, and we know that we take a sample and we can sometimes make an inference. So let's say that I want to estimate the average age of students at Marine City High School. So I could do that using the whole population, or I could take a sample of 50 students and find that sample mean. Let's say in this case, my sample mean for that N of 50 was 16.3 years. So X bar was 16.3. I can then infer that the population is also 16.3 years. This is called a point estimate. So this is how confident are we that the entire school's average age is 16.3 years. So this is where we go in Chapter 7. So there's a couple assumptions that we have to make before we can do these confidence intervals. The first one is that the samples are randomly selected. We've been talking about this for all year, right? We want a random sample. And the second thing is we always want our sample size to be greater than or equal to 30 or know that we have a normal distribution. So in this case, I am guessing that we probably don't have a normal distribution for our average age of students at the high school. But notice that my N is greater than or equal to 30. So section 7.1a, let's get started with confidence intervals. I'm going to point this out and you're going to think I'm being annoying, which of course you would never think about me. However, I want to make sure I point out in the title of this section, sigma is known. We know the population standard deviation. Sometimes we don't. So we need to make sure that we see, do we know sigma? Do we know S? What do we know? So the first thing, let's talk about a confidence interval. So a confidence interval is a specific numerical estimate. The average age is from 12 to 19. Right? So it's a specific estimate of a parameter. Remember, parameters are for population. So the parameter in the example that I used was the average age of a student at the school. The best point estimate for our mean is our sample mean. I put sigma here. This should be mu, right? The best point estimate, the best way we can estimate the population mean is to use a sample mean. Kind of common sense there. So we take means from our samples. Everybody knows mu and X bar by now. We do use the sample mean because X bar varies less than other statistics. We could use a point estimate like median or mode, but those vary more. Remember, they are less tolerant to things like outliers, stuff like that. So we use the sample mean as our point estimate for our mu. And don't forget, our X bar usually is somewhat different from mu because of sampling error. We just can't get the perfect representative sample. So we know we're going to have a slight difference. So it's looking at that slight difference and looking at a margin of error. So 3 properties of a good estimator. I left all the words up here for you. The first thing, the expected value or the mean of the estimates obtained from the samples equal the parameter. So basically it's unbiased. It's a good sample, representative. For a consistent estimator, as the sample size increases, the value of the estimator approaches. So X bar starts to approach mu. So it's consistent. Remember that central limit theorem. More and more and more samples, we get closer, our mu and our X bar. And number 3, of all the statistics that can be used to estimate a parameter, this estimate has the smallest variance. So it's pretty efficient. So we just need to make sure that we've got an unbiased estimator, a sample, we've got consistency, and we've got efficiency. Basically, we are looking for the smallest variance or the smallest differences between our true mu. All right. So an interval estimate. This is where we're starting to get down to what this looks like. So it's an interval or a range of values used to estimate the parameter. Remember the title of the section said we know our population standard deviation. We don't necessarily know what the mu is. So this is an interval or a range of values used to estimate. It may or may not contain the value of the parameter being estimated. Maybe our mu does not fall in that. Maybe we've had a bad sample. That can happen, and we're going to use that more later, but it may or may not contain it. So an interval estimate for the average age for all students at our high school, let's say that I knew that our margin of error, it's 16.3 was my estimate using my X-bar, and I'm going to say it's plus or minus 0.4 years. Well, the 0.4 years is my margin of error. So I can use that margin of error to figure out an interval. I know that the ranges of ages are between this and this, so I actually do the math. I do 16.3 minus 0.4 and 16.3 plus 0.4, and I end up with a range of values from 15.9 up to 16.7 years old. Notice in the middle of that interval is mu. So my 16.3 was my X-bar. Using my X-bar and my margin of error, I can say, well, the average age for all students at this school is somewhere between 15.9 years old and 16.7 years old. So that margin of error is something that we're going to need to calculate. We're going to know what our X-bar is, and we're going to calculate the margin of error. And then we're going to write ourselves an interval estimate. We're going to say, well, we think based on the information we have, we think that our true mu, our true population mean, is in between these values. So let's talk about confidence intervals or confidence levels before we get going on the actual calculations. You have to know a confidence level. How confident are you going to be? So a confidence level really is a probability that your interval estimate will contain your parameter. So that's what was the numbers? I can't remember. The 15.9 to 16.7, how confident are we that the true population average age is in between those? So remember, I left the fine print in there. There's a large number of samples, at least greater than 30, and I used the same estimation process. I did everything consistently. This is, a confidence level is actually a percentage stating how confident you are that your interval contains mu. So we'll do a lot with 90% confident or 95% confident, 99. We want to be pretty confident, right? This is a probability, so it's a percentage. If it's a probability or a percentage, 95%, if I'm thinking z-tables, I'm looking at 0.9500, right? That's my area under my curve. Remember, everything kind of comes together. This is our degree of confidence, and it must be assigned before we make any interval. You can't go forward if I don't tell you how confident I want you to be. So I'm going to tell you, I want you to be 98% confident on this. If I don't tell you, I screwed up, so please ask me. And I thought I had another bullet in there. Maybe it's after. So our interval for 95% confidence is not as wide as our 99% confidence, because as you increase your confidence, you have to have a wider interval. If I say I want you to pick a number between 1 and 100, I could say, well, I'm 100% confident that your number is between 1 and 100. I'm only 50% confident that your number is between 25 and 75. So as I increase my confidence level, I have to increase my interval because I have to have more room for error in there. So let's talk about our confidence interval. So again, it's a specific interval estimate. We use our sample data. We use our standard deviation, population standard deviation, because it's known, and we mentioned that in the title, and we use our specific confidence level. So margin of error, this is a nice formula, right? E, margin of error is an E, capital E, is equal to, don't be overwhelmed by all of this business right here. E is equal to z-score of alpha over 2 multiplied by our population standard deviation over the square root of n. Z-score of alpha over 2, that's a number we're going to replace, multiplied by our sigma over the square root of n. I'm not sure why I said it was called the margin of error, since that's under the margin of error. This is the max likely difference between your point estimate and your actual value. Just like in that example, we said 16.3 was our point estimate, and then we could go 4/10 of a year on either side of it. So that's that margin of error. And you might be wondering about the alpha. That's the only new thing I think we haven't talked about. Alpha is equal to 100% minus the confidence level. And we're going to turn that into a decimal. Because technically, that's the area under a curve. So alpha is equal to 100% minus the confidence level. All right, and here comes the biggie. Here's our formula for the confidence interval, and if it looks overwhelming, I want you to note the repetition. I'm going to highlight this margin of error formula right here. So z of alpha over 2 multiplied by our standard deviation over the square root of n. So in the middle, I've got mu. So I could go this much on either way of mu. Notice I'm going to take my x bar minus that margin of error and x bar plus that margin of error. So minus E, mu is in between, x bar plus E, if that helps you to see what the busyness that's happening there. So it's really just a plus or minus formula. We take our x bar, we find our margin of error, and we add it and subtract it. Again, remember, we know our standard deviation for our population. So let's do some practice. Let's do some looking. This is going to require a little bit of z-table work. So please make sure you've got your z-table. That is not going away. So let's just start off with our values. So how accurate do we want the population mean estimate to be? So in the first example, find the values for a 95% confidence level. So 95%. So first of all, alpha is equal to 100% minus that 95. So that's 5%, right? Then notice in our formula, it was z of alpha over 2. Well, we're literally going to do alpha over 2. I should have written down then 5% is like a 0.0500, right? So basically what we're saying is if we want to be 95% confident, we are, I'm just making this up here, this is 95%. So I have 5% left for either of these two tails. Because it's symmetric, a normal distribution, I know that that's split evenly because it's symmetric. So I've got that 5% or 0.0500. If I do divided by 2, that tells me how much I've got for either end, right? So that's like a 0.0250 down here and a 0.0250 down here. So I'm going to divide that by 2. So then I jump into my z-table and I find, or as close as I can, to 0.0250. Is that going to be on the positive side or the negative side? Everybody knows the negative side, right? So when I look up an 0.0250, and I always put the extra 0 on the end so I don't mess up, That one is nice and exact. It's negative 1.96. There is the value that I'm going to actually put into the formula when I calculate my confidence interval or my margin of error part for both sides of that inequality. So that one was really nice and neat. It came out perfectly. We all like it when the z-value comes out perfectly. Let's find the values for a 90% confidence level. So we're 90% confident. So again, what that looks like is 90%, right? So alpha is equal to 100 minus that 90%. So 10% or 0.1 thousand. But that's split evenly on my normal distribution, right? So how much do I have for each little table or each little side of tail on my graph, my normal distribution? That's going to be like a 0.0500, 05, right? Oh, by the way, that negative 1.96, I didn't look up the other side because it would be positive and negative because it's exactly symmetric. So that's why I only looked up the one side. I got a little lazy there and forgot to tell you. So my z-value for my alpha over 2 is 0.500. So I'm going to find 0.500 on the negative side of my table, jump into your table, and it's directly in between two values. I need to add something, and I'm sorry to confuse you or change it up on you. Because we are calculating margin of error, if you are between two values on your z-table, go to the larger z-value. We've only gone to the smaller until now, but we're going to go to the larger value because when we do the calculations, multiplying by a larger number gets us a larger margin of error. Just a little more squeak room in our confidence interval. So when I look up an 0.500, I am in between two values. I lost it. I'm in between a negative 1.64 and a negative 1.65. I just think absolute value 1.65 is larger. So I'm going to go with the negative 1.65, put the negative on there. That's going to be my z-value that I put into my margin of error formula that I put into my formula when I do the plus and the minus. So we're still using our z-tables because remember, it's a normal distribution. So those things just never go away. Larger z-value. This is the number one thing. I switched it up on you. So make sure you make a quick note on that one. I didn't even have it on the notes. I wanted to make sure. So now let's take that and let's do a problem where we actually construct a confidence interval. Do not be scared by the word construct. It's just, you know, a word that we use when we are doing this. So it says to construct a 95% confidence interval for the population mean. A sample of 50 cars had a mean time on a dealer's lot of 54 days with a population standard deviation of 6 days. So I'm going to just jot down over here. What is my sample size? That's 50, right? What is my x bar? What is my sigma? What is my z-value of alpha over 2? If we could get all that, we've got everything we need to go into a formula. So x bar, the sample had a mean time of 54 days. The population standard deviation is 6 days. And my z of alpha over 2 comes from this 95% confidence level. So alpha is going to be equal to 5%. Divide that by 2. Thankfully, I just had you do that on that last example. When we did a 95% confidence level, the z-value, I believe we came up with a 1.96, right? Negative. So here's the thing. When I set this all up, look at that formula. The mu is in the middle. I always set this up like this just because I think it's easier. So I'm going to put my mu has to be somewhere in between these two values. So it's x bar, 54, plus, nope, that's a minus on that side. 54 minus, this one's 54 plus. X bar plus and minus. It's the z of our alpha over 2, so 1.96. It's already got a minus out in front of there, times our standard deviation over the square root of n. So 6 over the square root of 50. This one I'm just going to sort of disregard because I know that 1.96 would be on the negative side, 1.96 would be on the positive side. So just stick your 1.96 in there, and then completely identical. The only difference in this formula between these two sides is one is a minus, that z times the sigma over square root of n, the other one has a plus. And then it's just down to calculation. So two separate calculations. Do not try to do these at the same time. So if my calculations are correct, I ended up with a 52.3 on this side. Please hit pause and check to see that you get a 52.3. Is less than mu, is less than, that looks like a 55.7. So I can be 95% confident based on my sample that the population average time of a car sitting on a dealer's lot is somewhere between 52.3 days and 55.7 days. So that's what we're saying. Since we don't actually know the population mean, our best guess it's somewhere between those two values. The rounding rule, if you're using raw data, which we are, right? We're saying 50 cars in 54 days. Standard deviation is 6 days. Round to one more place than our original data. That's why I went to a 52.3 and a 55.7, one more decimal place than our 54. Basically, look at your X bar. All right. So hopefully that isn't as confusing as the formula looks. I think the trickiest part is to find your z of your alpha over 2, remembering to divide that by 2, and then go into your z table. So margin of error, your E calculation, depends on your sigma. I have to give you your population standard deviation. It depends on your confidence level. I have to tell you what percent of confidence I want you to have, or I could tell you alpha is equal to 5% or 0.05. Right? Either way is the same thing. So I could say 95% confident, or I could be sneaky. I could just say alpha equals 0.05. We know that that's 5%. We know that's a 95% confidence level. And your margin of error, E, also depends on your sample size, your N, all those things I need to give you. So there is one problem. There's one more example in the notes. I think we'll save that and we'll do that one together just to make sure everybody's good. That is it for section 7.1a. There's a lot here, but the only new thing is the alpha over 2, the confidence level. The rest of it is making sure you know how to use your calculator. So 7.1a, thanks for sticking around. Have a fabulous day.